So good morning and thank you for attending. I'm glad to be here in order to introduce the geotechnical session. For those who are wondering about this guy, my name is Clément Galandrin and I'm head of innovation for the CAN company, member of the cluster Andura. CAN is a contractor specialized in natural hazard protection works and also part of the mine project inside the working group Geotechnics. I'm happy to lead this session with Sylvain Marie. Sylvain leads the BIM expert team at Railenium, the French Research and Development Institute for Railway. He has been involved with Building Smart since 2013 as a technical expert in charge of interoperability issues and semantics management. So the topic of the session is geotechnical information modeling. We have seen since yesterday the deployment of BIM solution in the infrastructures sectors. This morning's presentations will focus on the extension of OpenBIM to geological and geotechnical data. How to implement the BIM initially applied to man-made objects of industrial origin to the natural environment on which our infrastructures are based and with which they interact. The first presentation is Geotechnical Data Standardization for OpenBIM, the MIND GT15 initiative. We'll have two speakers. First one is Isabelle Alphon. She's working at the French Geological Survey, BRGM, as a geotechnical engineer. She participates in the MIND project GT15, which deals with geotechnics. Second one is Michael Boffis. He is also working at the French Geological Survey as data architect and leads the MIND Geotechnic Working Group. He also participates actively in international standardization, especially in the Open Geospatial Consortium. So Isabelle, Michael, I let you go for the 20 minutes presentation.
Yes, thank you very much for this kind introduction, Clément. Do you see my screen? Yeah, that's a good thing. So I will try to go into presentation mode. Is it okay for you?
Yes.
Is it full screen for you? Fine. So, as you introduced, we will deal with the MIND GT15 or WG15 working group regarding geotechnics. In the MIND projects, some projects you already heard about, certainly in this InfraBIM Open conference. So I will briefly start with the status about BIM in France. So you had already introduction about what is BIM, targeting a digital twin of the construction, becoming more and more present for infrastructure, road, rail, bridge, tunnel, earthworks, and geotechnics. So what you must know is France is among the leaders in BIM. So this has been presented in other presentation, maybe in the plenary session also, supported by the French ministry. France is very active for building some open standards for BIM, especially for infrastructures. And there is one big project that helped to do that, to federate people, is the MIND project. So there is also something that helps to provide and develop interesting and useful standards is the fact that in France we have big infrastructure projects, especially in the domain of underground infrastructure. So you may know, for example, the tunnel between Lyon and Turin, also the Grand Paris Express that is building some subways lines, and also a project by Android to store radioactive waste. The MIND Geotechnics, so Working Group 1.5, is one of the group in the MIND that is dedicated to extend the standards for OpenBIM, and this one is dedicated to geotechnics. So it started in 2019, and we are about to close. I mean, there is still a report to write, but we are about to close. In this group, there were about 20 people, mainly geotechnical engineers, and we had some weekly meetings in order to discuss how to arrange the standards for geotechnics. So among the people that participate, we have some research and public domain, some owners, many engineering companies or consultants, but also contractors that are very active in France. The philosophy of the group was to propose a soft transition to BIM. I mean, the idea was to build on today's practice instead of enforce, reinvent new practices. We want to propose something that will be feasible and possible to implement. That's the key thing for us, not only speaking about interoperability, but making it happen. Most members are geotechnical engineers, so we have people that have some requirements and we want to fill those requirements. The proposal that we build is something that is for all. I mean, we target a worldwide application, not only France, but of course it was built from French people in French projects. And we want also to address every kind of project, not only the big one like Grand Paris Express, but also some smaller projects. We think that BIM must be applied for every kind of project, and I think it will become mainstream in the future. So the idea is not only target the projects that have 3D geomodeling, for example. We also target projects that still rely on 2D modeling. Standardization versus interoperability. Yeah, what we want is to enable to describe what was done, not enforcing the use of specific parameters. This means that by the technologies and the solution we provide, we try to build things that enables you to better exchange what you did, not saying, okay, because the standards need this, you have to put it in it, and if you can't use the standards. The idea is to be able to use the standards independently of this.
Yes, as said by Michael, our main intention was to be as close as possible with our daily practice of geotechnical engineer, to express all expectations of the group and to bring answers to very pragmatic questions, such as how to organize and classify the geotechnical information, in which kinds of representations, what are the components of a geotechnical model, which properties do we want to associate to these components, how to keep the origin and traceability of data, how to express the geotechnical uncertainty, how to link the structural design to the geotechnical model, how to integrate risk management. First of all, it was necessary to have the same understanding of what can be a geotechnical model, a geotechnical BIM model, and what do we want to put into this model. So we agreed that a geotechnical BIM model should include 3 sets of objects: the geotechnical raw data, like boreholes here in green on the slide, with their associated test results, but also all kinds of input data. No, the previous one, Michael. The geotechnical interpreted objects, like geotechnical units, which you can see here on the slide. Geotechnical unit, that means the soil layers with their geotechnical properties, but it can be also hydrogeological unit, piezometric surface, cavities. And the third set of objects are, of course, the structural objects resulting of the geotechnical and structural design, like, for example, tunnel lining with its associated technical characteristics. So it was decided to organize the data of a geotechnical BIM model exactly in line with the AFTES recommendation for the organization of tender documents, the GT32R3, which says that the technical documents are composed of 3 books, Book A, Book B, and Book C. So it appeared very logical to transpose directly this organization for the numerical data structuration with 3 sets of objects. Book A, object of row of geotechnical investigation. map zone, boreholes, and all kinds of input data. Book B, which contains the interpreted objects like geological units, fault, geotechnical units, and so on. And Book C, which would include, of course, the design structures and also typical design section, typical design area, geotechnical zone of influence, etc. So the following step consisted to establish a comprehensive list of objects of each book. The approach chosen by the working group was to use our own examples of real projects using different tools and representations and make a list of the represented objects. Here are a few examples. Each object is identified with a sticker, a color, and a name. For example, here on the right picture, you can recognize a Plaxis output screenshot, and we put the stickers of the geotechnical unit, which is an interpreted object, the fluid body surface, the piezometric surface, the existing constructions, and some structural objects of the design, like the diaphragm wall or anchorings. Here we can see three other examples that were used to identify the objects. And it is also interesting to note that in the geotechnical practice, different kinds of representations and softwares are used. Regarding representations, we can find maps, plan views, cross sections, and about the softwares. In geotechnical practice, of course, we use CAD software, calculation softwares like finite element software, but also geological 3D modeling softwares. So it was we found different and very various tools. The result of this work is therefore a comprehensive list of identified objects. You can recognize all the stickers needed in a geotechnical model. It is worth noticing that some of them are already identified in existing standards like OGC standards. For example, standard geoscience ML and groundwater ML2, and other objects are new and need to be created. And among these features, we can classify them. As you can see, the green objects at the left side of the picture are typically Book A objects containing raw data information, and the others are interpreted or designed objects and will be associated to Book B or Book C. The next step after identification of objects was to list all the properties to be attached to these previous objects. For instance, we can see here, so we prepared a big Excel file containing all the possible geotechnical properties. And here you can see the properties associated to the rock matrix of a rock mass geotechnical unit. Each property in our file is named in French and English, with a comprehensive definition in French or English, with its usual symbol unit as well as its link to the geotechnical feature. An important concern was to keep also the traceability of the data. In geotechnics, as you know, a given property can often be defined using different methods of test procedures. So we all find very important that a property should be associated with its measurement procedures. So in our big Excel file, we also add a sheet with a list of all the existing procedures and tests used in soil mechanics and rock mechanics. Now we come back just for example to one of the most important new objects to be created, the geotechnical unit. Many discussions took place in the group to define the geotechnical unit. Finally, in order to reflect our geotechnical practice, it was decided to define three kinds of geotechnical units: the soil-like material, which is associated to soil mechanics parameters like identification parameters or mechanics parameters. The rock mass geotechnical unit, which is characterized by three sets of properties: the properties of the rock matrix, the discontinuity properties, and the equivalent rock mass properties. And the third kind of geotechnical unit, which is the standing alone discontinuity, which may play a role in some geotechnical problems. This one being associated with its discontinuity properties. As evocated previously in the questions I've listed at the beginning, one of the questions was how to express the geotechnical uncertainty in the geotechnical beam model. The uncertainty is generally assessed in the interpretation stage and thus has to be included in Book B. But as you know, the subject of uncertainty in geotechnics is very wide. And we don't have the pretension to bring a definitive answer to all the questions. But regarding the way of implementing the subject of uncertainty, two proposals are made. For uncertainty or variability on the geotechnical parameters, it can be simply implemented by using statistical distributions for geotechnical parameter, or a set of statistical values like minimum, maximum, median, average, etc., or more simply using brackets of values. And for the geometrical uncertainty, we propose to follow the AFTES recommendation and use different modes of representation, like for example on the right side of the picture, when the uncertainty concerns, for example, a contact between two layers, we propose to draw three lines instead of one to show the range of variability. So at the end, it is possible to produce a federated geotechnical and structural beam model by putting together the objects of Book A, the raw data, the objects of Book B, the geotechnical interpreted features, and of course those of Book C, the structural design objects. Here you can see on the right side an example of a typical section of a Grand Paris Express underground station, which shows together the geotechnical objects from Book B and the structural design objects from Book C, synthesized into a typical design section.
So what Isabel presented is already a lot of conceptual proposal. I mean, reflections from what we imagine to be the good solution in order to exchange geotechnical data. And then there is a moment when we have to go into implementation, when we have to propose solutions that enable to expose the data the way we imagine. So there are already visible contributions from the MIND GT15 or WG15 that are available. We have some geotechnics vocabularies that came to feed the BRGM registry. So that's a placeholder for the vocabularies that can be useful for geoscience in general, but especially here in geotechnics. So this is already available, and we are doing other activities in a project called Open Geotech in order to prepare a new consultation interface, make it prettier and more accessible. And we're also working on solutions for declaring new and proposing revision of vocabularies. Another way we wanted to go is into dissemination and internationalization of our work. So there was in 2019 a workshop that was held in Paris called Geotechnical Data Synthesization Workshops that aim to federate people from both the Open Geospatial Consortium and Building Smart International and other people involved in geotechnics. So we had in mind this schema we have at the right, that saying that we should have a kind of forum in which we will define how that geotechnical data should be exchanged. And this forum should be the connection of people representing different organizations, different communities. And what was made from that is we started with IFC Tunnel Geo subgroup that to me is where this philosophy was applied, and in which we discuss about how the IFC geotechniques should be developed in order to enable the connection with OGC standards and enable the connection with other things. So that was in 2020, 2021, and now in 2022, we are reaching a new step that is going into the other branch, that is through Geoscience American Group. And you can see also that there is a new member that is this TC222 from ISSMG that is now existing. And I think we are close to build what we imagined in 2019. So there is a project. So one thing we wanted to do is to do some kind of digital continuity for geotechnics as a BIM era. So you have seen in the what Isabel presented, that we exchange different kind of data, and some of them may be already accessible and defined in GIS. And so the idea was to enable to use it instead of retyping it. That's the idea of this project. And so we wanted to launch an activity about that in order to connect what the Building Smart International standards can do, so IFC standards, and also what the OGC standards can bring. The idea is to reach fair geotechnical data. And this project is happening now. So it was just launched at the end of 2021. And we have a nice program that you can see on the left on different things we want to address. So for 2022, we have the launch of two calls for participants, two major ones. One is an OGC activity in connection with Building Smart International in order to address what I presented on the previous slide. So you can see this call for participant is available now. It was launched yesterday. And the idea is you are welcome to join us to work on this. And the kickoff is expecting at the end of January or early February. And on the other side, we have this creation of this technical committee 222 about geotechnical BIM and digital twins from the ISSMG that have just been launched too, and that will have a first meeting expected in March. So for the geotechnical one in OGC, I will be the leader of it. And for the one of ISSMG, this is driven by Magnus Romoen from NGI, and I will be the vice chair of this one too. So conclusion and next steps. Thanks to Isabel, you had an overview of what is the proposal of Mine Working Group 1.5. A conceptual model including objectification and a lot of associated properties. That was a major action of our group. These things were shared and supported by all of these members presented in Syntec Engineering, CFMS, and we are working to finalize the report. And the second thing I would like to highlight is 2022 will be the year of geotechnical data standardization for BIM and GIS. I think never in the past we've been so close to reach that goal. I mean, having those people that want to work together and to build this, and also the capacity to do it. So I'm quite optimistic that we will do it. So there are different things that will be done to reach digital continuity between GIS and BIM. So there is an upcoming new version of AVC 4.3 that will include new concept updates for geotechnics. We will work on this extension of geoscience standards in OGC, and we also promote the use of OGC APIs to access GIS data from a BIM environment. Will be things we will do in 2022. And if you like the two, we also have three here. Collaboration with ISSNG TC222 to ensure the connection with the scientific society. So this also where the people from the scientific societies meet people that are doing standards. And everything was based, but not exclusively, on the work of the Mine Working Group 1.5. So thank you for your attentions. If you like to contact either me or Isabelle, you have our address. We are here on the behalf of the group that is composed of members of the organizations that are below. And I wanted also to highlight some document we are preparing and that will be shared very soon. That is a white paper about how we imagine digital continuity for geotechnics should be done at the BIM era. So again, thank you for your attention. Happy to answer some questions. Et si vous préférez que l'on parle français, c'est aussi possible. Il n'y a pas de souci. Bonne journée.
And maybe we can add that a deliverable on regarding all the work of GT15 is currently in progress and will be available soon, I think.
Yes, exactly.
Thank you, Michael and Isabelle, for the first presentation of the day. Is there any question in the room? Yes. We have one.
Yes.
Hello, can you hear me?
Yes.
Okay. I'm Olivier Cuchet from Vinci Construction Grand Projet. I have actually two questions. The first one is, having considered this concept of book A, B, C, which is a typically French way of defining geotechnical information for a project, isn't it a drawback in terms of internationalization of all this? What are the discussions you are? Because I understand that the work of disseminating has already started. What are the reaction for that?
Yes. So regarding book A, book B, and book C, that's something was, in our core proposal in mind for the French people. And when we presented to the people of IFC Tunnel Geo subgroup that are addressing geotechnics for IFC Tunnel, that are not only French, they are not so much French, they really like it. And to be honest, book A, book B, book C is now the, let's say, international way to define how the data will be exchanged in the core proposal for IFC Tunnel. So that's something we presented in 2019, and now the proposal for IFC Tunnel is built on this concept separating book A, book B, and book C. So that's something that come its way, and yeah, we are very happy to have been able to convince people of its utility.
Okay, and second thing, we all know that this process of having a general agreement on each and every typical parameter and data and so on might be very long. Yes. Do you consider maybe focusing on the data which are actually used by, a range of the most used software that are in use in the world? I don't know if this may limit a little bit the scope, the general scope of defining the data, but which will be of much added value to the people who are working with this data, actually, the engineers who are calculating the structures and
Yes. Yes, I understand. So in this project and also in IFC Tunnel, the idea was to build something that is a conceptual model. It means that is agnostic from the way it is implemented. It's the way that geotechnical data are thought and also exchanged. And what we build is some kind of framework that enable people with some technologies be able to describe what it did. So that's for the vocabularies, for example, we have a huge list and they will never be finished. And the idea is to enable people to say, okay, the parameter I use is this one, and you can have the reference to it and say what it is. And if it is not into the registry, you can propose to add it to the registry so people will see what you have in mind, and it will. And finally, yeah, that's something that will be built step by step, and that will not enforce you to use a specific one, to say, okay, if I don't have this software, then I will not be able to apply it. That is not our goal. Our goal is to enable you to work with what you already have and just to explain what you did, and that's what we propose in it.
Another question in the room? There is no one on the chat. Okay, so it's okay for us, Isabelle and Michael. Thank you very much.
Thank you.
You're welcome.
See you.
Yes.
Bye-bye. See you
Bye-bye.
soon.
So next presentation will be being certain on the geotechnical uncertainties using the GeoBeam concept. It will be, the speaker will be Mats Svensson from Sweden. Mats is business developer for Tyrant's company. He holds a PhD and is an expert in geophysics for engineering and environmental purpose. Now his work is focused on implementing geo-related R&D achievements within the infrastructure and environmental industry. He has prepared this speech with Olaf Freiberg, BIM and GIS specialist at Tyrants.
Okay, can you hear me?
Yes, Mats, we hear you loud and clear. Welcome to Lyon.
Yeah, thank you. So I'll present this project, which is called Certain Geotechnical Uncertainties, which is another application of the GeoBeam concept, which we have presented a number of times on this conference before when it was in Finland. Just to give you a teaser of where we will land at the end, what we have done is we have developed an uncertainty algorithm that produces 3 different models and an uncertainty map. And we have focused on the bedrock model. So as you can see on the left-hand side here, the green model is the most probable bedrock, and to which the uncertainty map on the right-hand side belongs. And I will come back to those later on. But let me start with the reason why we need uncertainty models. Geotechnical models are always a discussion, especially in large infrastructure projects. And differing geotechnical conditions compared to what we came up with in the design process and in the actual building phase is always a reason for claims. So by having a proper uncertainty model, it will be possible to optimize planning of the investigation program whenever during the process it's needed. So being certain on the uncertainties, that will reduce the number of claims. This is the background of this R&D project. But let me start then with the method which we normally use in our geotechnical daily life, you could say. We work in our company with a totally closed digital chain, which means that we always start with our database, the GeoBeam database, where we check, do we have any information from this area before? If so, we do a geotechnical interpretation, we do a 3D model, a geomodeling, and then we use that as a basis for the first field investigation. What we have added in this project is we have added that we bring out from the database a basis for an uncertainty calculation. We do that uncertainty calculation and already in this phase come up with a geomodel which includes uncertainties of this, in this case, specific bedrock. And then we use that as a basis for the complementary field investigation. We carry out that field investigation, that data goes into the database again, and we can update this process. And theoretically, we could loop this in a number of iterations until the uncertainties are low enough regarding to what the client wants or whatever. So once we have finalized the uncertainties are low enough, we kind of lock this geomodel, which then comes with uncertainties, and we send that further on in the process for further design work or whatever it will be used for. That is the methodology we use in our daily life, so to say. So in this project, we have developed an algorithm, and that consists of two parts. First, the individual uncertainties on each investigation, mostly geotechnical soundings with the drill rig, and we also use the distance to the nearest investigation. Those are the two main features that build up the algorithm. In the algorithm, we use kriging for the actual modeling, and the methodology for the uncertainty calculation is Monte Carlo simulations, and in this case we have used 1,000 models, and that is the model is a modified Gempi method, which is developed at the University of Aachen in Germany. You can see the reference there. And the other part, as I said, is the distance to the nearest investigation. So by using those two features, we start the calculation, and the result is, as I showed you earlier, these three models, where the green one on the left-hand side is the most probable bedrock. And to that most probable one, we produce an uncertainty map, where the reddish colors represents, this is the areas where we have the highest uncertainties concerning the altitude of the bedrock model, and the green areas are where we have the lowest uncertainties. And then on the left figure, we also have an upper bedrock model and a lower bedrock model, and those are in between those two models. We have a 95% you could say certainty or where the real bedrock surface is. And you can also see some red areas here. That is a surveyed rock surface, which we have been lucky to have access to in 5 different ongoing projects, which I will show you results from later on. But this is the kind of the data set that we produce with our uncertainty algorithm. before we get into to see how good is this algorithm, I want to show you the reality. This is a picture of a typical Scandinavian bedrock surface, which is uncovered. As you see a little bit of the scale there, 3 meters. And a typical investigation program in an area like this, in Sweden at least, would be maybe one, at the most 3 sounding points. Thinking of that frequency of available data, there is no way you should expect any better precision than, I would say, half a meter, maybe a meter. Somewhere in that space is what we should expect the algorithm to hit. So how good is the model? We have been able to check that in this project. The red line is the bedrock model, the most probable one that we produce. The green one is the surveyed uncovered bedrock. So you get 2 misfit volumes. Sometimes you're in some areas of the area, our model is a bit lower than the actual bedrock. Then we get a bit more rock to blast, and on the other way, in some areas our bedrock model is a bit lower, and then we need to dig a bit more soil out. So as I said, we have been lucky to have 5 cases where we actually have the truth, where we have uncovered and surveyed bedrock surfaces. And those are in various places in Sweden. One in the case 5 is in the upper north, and then 4 other cases further south in Sweden. And those are all quite large infrastructure projects, you could say. The 3 first ones are road projects, the 4th one is a railway tunnel project, and the other one is a large industry area. So if we look at the misfit that we have in these projects, case 1 to 5, the first row here, total misfit, you can see we have on the left, in case 1 we have 0.4 meters and 0.5, and on the case 5 we have the biggest misfit, 0.9 meters. You can also see on the 2 other rows what they builds up of more soil or more rock. But in between 0.4 and 0.9 meters, that is what we have in the misfit in those areas, which corresponds very well to what we should expect, I would say. So we are quite confident in our algorithm here. Just to quickly go through the different cases, the first one, if we look at the right map, the uncertainty map, you can see there is a lot of blue areas, and a few parts of the area is reddish, and those are all or most of it is in the outer parts of the area. If we zoom in on the scale, you can see the uncertainties goes from 0.1 meters to 1.2 meters at the very borders of the area. There's a small orange or yellow spot in here. I will come back to those. Case number 2, same pattern, red in the borders and a few yellow red spots in the middle of the area. This one, case number 3, is a bit more interesting. You can see we have some very red areas in the middle of the area, which is actually quite good investigated. And if we zoom in, we have still 0.1 to 1.0 meters of uncertainties. But if we look at one of those red points here, this is a typical one. In the database, we notice that this sounding point has actually no stop of the sounding depth, which means the field crew hasn't followed the standard for how you carry out this method, which means here you get another quality check of the data. Actually, you could backtrack and go back to see why. What is the reason? Why do we actually have those big uncertainties, individual uncertainties on these spots, on these soundings? And we can see we have a problem. So we may take away those from the and do the calculation one more time. Case number 4, same pattern. In case number 5, same thing again here. So we are quite confident that our algorithm is doing a good job here with a precision of between 0.5 and 1 meter. But I'd like to highlight 2 interesting results from this project here. The first one is we normally do a lot of soundings and sampling with our drill rigs in local, very specific positions. And in between those positions, we have very little information. And this is this is actually from case 4, previously the railway project on the west coast of Sweden. We have a number of soundings, and we did this uncertainty calculation based on only the borehole sounding data. And as you can see, we have quite a lot of red areas, which shows on the scale here we have uncertainties of 0.6, 0.7 meters, which is after all quite good as it is. But look at what happens if we add geophysical data. We have access to 3 seismic lines here, which means we have below each geophone, we could interpret the level of the bedrock, which we have done. We have no possibility to add a specific individual uncertainty below each geophone, as we can do with the sounding data, where we can actually look at the different soundings. So what we have done here, we have added a general uncertainty, individual uncertainty of 20% of the depth. But still, we can see that even if we have large individual uncertainties on these seismic data, the frequency of data points, the number of data points, is so high that that kind of overrules the high individual uncertainty. So it's very obvious that geophysics is really adding value regarding lowering or being less uncertain on the bedrock level here. The map is much bluer for a non-geotechnical guy, you could present it as. The other thing I'd like to highlight is a borehole is not always a guarantee for good quality of a good model. I have highlighted a circle down here on the left-hand side. You can see there is a red spot inside a generally green area where we also have quite a lot of sounding points, I would say. And why is that? Well, it's the other way around compared to the geophysical example on the last slide, previous slide. Here we have large individual uncertainties, and that in the sounding points, and that overrules the large number of boreholes. And how to use that information? This is actually a very good way of how you could use uncertainty maps. You should use it as a basis for decision of changing method. It's obvious that those soundings, this method is called soil rock sounding in Sweden, and that is normally used as we reckon as the best method for defining where the top of the bedrock is. In this case, it shows that that's not the case. So we need to find a better method. In this case, we suggested core drilling. So one could ask, what is BIM in this? Is this really BIM? Is it open, as the conference is called here? I would say we use a totally closed digital chain from the very beginning of the process, the planning, all the way to the presentation of the 3D model and the bedrock model here, including the uncertainty maps. All data is the algorithm gathers or picks the data from the database, and the data is classified in a BIM manner, you could say. And each data point in the database, it carries information of its individual uncertainties. And I will also highlight that in these uncertainties, those are specified by the most often the field crew, who are the best ones to actually feel on the machine and out in the field. Now, is this a proper level of the bedrock, or is it something else? Are we uncertain, and so on? So they add in these individual uncertainties into the database. And we have a totally automated process from basis for calculation to 3 models and an uncertainty map, as I call it here. So there is a lot of details that actually fits the BIM definition here. Is it open then? Well, the algorithm is programmed using Python code. We use ordinary Python libraries and so on. And the algorithm will be published in the final report in the coming month, or maybe in March later on. So I would say this is also an open tool. To finish this presentation, I'd like to show you as I see as the value of being certain on the uncertainties, in this case, the bedrock. You could use it for optimization of an investigation program. By doing that, you always get the most value for the money. You can locate your boreholes or your geophysical lines where you have at each moment where you have the highest uncertainties to complement the previous model. And by being certain, even you know you're always uncertain, but you know how uncertain you are. That gives you a feeling of you always have control, which gives you a big confidence in the team during the project, and that is worth a lot of money, I would say. You get a possibility to have a clearer risk sharing in contract between the client and the contractor, and that as a result results in less claims, definitely. And I will exemplify that with this final figure here. This is a schematic of, in the middle, the most probable bedrock model, and the upper and lower most reasonable bedrock models. When you start digging and you uncover the bedrock, you get this green figure here. You survey the area and you get the true bedrock. And as you can see, this is normal case. In some areas, the true bedrock is a bit outside even the upper reasonable bedrock model. And in some areas, it's even a bit lower than the reasonable bedrock model. But having defined those borders with uncertainties already in the design process and during the contract phase, there is no problem giving the client has no problem giving the contractor extra payment for those volumes. No claim issues here. And in the same way, as long as the true bedrock is inside those upper and lower reasonable bedrock models, the contractor will get no extra payment. They should be prepared for this with their machinery and their tools and so on. So I'm pretty confident in that using this kind of methodology, this kind of uncertainty maps, would result in less claims in our industry. And that concludes my presentation.
Thank you, Matt. And thank you for being just in time. Perfect. Do we have questions? Yes, we have questions.
Yes, thank you for this presentation. It's a very interesting approach of of this question of uncertainty, which is a major topic in all geotechnical structures. My concern is that the parameter that you have analyzed here is the level of bedrock, which is, I would say, a one-dimensional parameter, considering one geographical point. You are either over the bedrock or below the bedrock, while in all geotechnical structures there are a number of parameters which needs to be considered, and it becomes much more difficult to define such range for each and every parameter that is needed for calculation or for defining excavation means or whatever. Do you have any clue on a possible way to expand this kind of analysis to a much larger number of parameters?
Yes, I have. In this project, we have this is one part of this R&D project. The other part is on geotechnical properties like shear strength and shear stiffness and so on. That type of more design parameters. But to start with the geometrical issues or the geometrical parameters, we have an idea of expanding these to like fracture zones or weakness zones, or groundwater levels, or that sort of geometrical features as well. It's just, I wouldn't say just, but it's another. You need another type of raw data for those types of calculations, but we could, I think, modify our algorithms to fit that those other geometrical features as well. Concerning the other part of the project, which I didn't present here, we have developed a dashboard which use multivariate analysis and for working or handling the uncertainties on the parameter shear strength, and that is more or less what we have done. We have designed a tool that makes the results from two PhDs projects in Sweden, which focus on this multivariate analysis, how to handle uncertainties on geotechnical properties. Just to make it more useful we have shaped a tool which makes it useful for the ordinary geotechnical engineer, I would say. And same way there, we have focused on the shear strength. We also have plans to expand that to friction angle or shear stiffness or other geotechnical parameters as well. And in that project, we have shown that we can, using multivariate analysis, we can increase with certainty, increase the design values with up to 20% when we use the Eurocode design rules and so on.
Thank you, Matt. We have a question on the chat from Joseph Carlin. The question is, what use are you making of GEMPI in your work? What is your experience here?
We started off by, we wanted to use all the features available in the GEMPI program or code, you could say. But we realized we're working on a scale where we have, let's say, down to 30, 40 meters in our road, railway, and tunneling projects, whereas GEMPI is developed for kilometer scale, deep fractures, deep scale geological features. So that's why we call it the modified GEMPI. So we have taken away some features from that code and modified it a bit to fit our area, so to say.
Okay, thank you. Last question in the room. I have one last. You end up with subsurface model representing the geological horizon with their uncertainties. I remember that 2 years ago in Tampere, you presented GeoBeam models with your database of geotechnical objects with the co-class definition. Are you able to link your uncertainty model with it to have a complete visualization of projects?
Maybe my colleague or co-author Olof, if you're on air, could you answer that question? If you could be unmuted.
Teamwork.
Yeah. I can answer that one. We have actually made use of co-class to represent the uncertainty on the different types of bedrock which we deliver from the algorithm, which is the upper and the lower and the most probable. But it's not as easy to, how do you say, classify each and every single uncertainty data point which we get from the algorithm according to co-class yet. So that is a job that is, that we are thinking hard of right now, to be honest. Yeah.
Okay, thank you. Thank you for the presentation, and we will pass to the third one. Thank you, Mats, and thank you, Olof.
Thank you.
See you in Tampere next year.
Yes.
Sylvain will take the lead for the two last presentation.
Thank you. We are quite good at the time. And we are going to the third presentation named, so once we have the slide, title for the third presentation is Geotechnics and Subsurface Information, Ontologies and Data Model of the ResQML v2.2, with examples of interoperable transfers between geomodeling, BIM, and GIS softwares. And this presentation will be done by Jean-Marie Léonard. Jean-Marie is a senior geologist and IT architect at Aegis. He has worked to develop software tools based on ResQML 2.2 for the use of Aegis Geotechnics. And he was a help on this work with Priscilla Labour, a geological engineer. So we have lucky enough to have Jean-Marie live on this room, but the presentation will be pre-recorded. We'll launch it and be ready to take questions.
The title of my communication is Geotechnics on Subsurface Information, Ontologies on Data Model of the ResQML version 2.2 format, with examples of interoperable transfers between geomodeling, BIM, and GIS softwares. My presentation begins by the context and history of our works with ResQML. Then after, I will present a general information of the ResQML version 2.2 format. Then I will detail you the conceptual data model with the world bore organization overview and the 3D geomodel organization overview. I will present the results of transfer tests on all Aegis projects. Now, our solution with ResQML is used in production. The first project was the Grand Lyon subway line E. And actually, at Monaco, we have a project of renovation of the Charles III district. And finally, the conclusion. Context and history. Previously, Aegis was importing boreholes information from Excel files, was using the GDM software to build accurate geomodels, was exporting boundary surfaces on 2D grids of S3, was importing these ASC files to CAD and GIS softwares. In 2013, the need was gather all this information in a standard way in order to deliver it seamlessly to BIM and GIS software, to find an interoperable standard for the underground. There was no EFC, but RescueML was already operational. Now a pair of RescueML documents produced by Aegis can gather all this information for a given study thanks RescueML Builder, deliver it on demand to the Autodesk Civil 3D BIM environment thanks RescueML CAD, publish it to GIS environment thanks RescueML GIS under ArcGIS Pro. The general information on the RescueML format. RescueML is a standard for geomodeling. Originally, this standard was designed by Energistics, a huge oil and gas industry consortium, to handle all geomodeling data and interpretations. RescueML supports the workflows. For Geotechnics, we need to exchange faults and horizons, wells born on their data, stratigraphic organization, and more. The RescueML format needs a pair of separated files, the first for the metadata and the second for the data. The first is the Energistics packaging conventions. It's an archive as a zip file containing two kinds of XML files. We have top-level element files. They contain the description metadata of any element of type, feature, interpretation, representation, and properties. A top-level element is identified with an UUID. We have also relation files that describe the relation between two top-level elements. The second main file is a hierarchical data format version 5. It's a structured binary file allowing to store the numerical data, such as the coordinates x, y, and z of the summits of the triangles of a thin surface, or for the values of pressure metadata or gamma ray measures. A system of reference allows us to find the data associated to a top-level element. The RescueML format defines the objects with a strong semantics based on the extended triangle of Ullmann. A feature element is the abstraction of a real object. An interpretation element is a possible interpretation of the feature element. We can have several interpretation elements for the same feature element. A representation element stores the topology and the geometry of an interpretation element. We can have different representations according to the level of detail. Then we have a hierarchical organization of the elements. At the summit, there are the features, then the interpretations, then the representations, and at the base, the properties. The RescueML version 2.2 conceptual data model. Here is the Welber organization overview. A top-level element inherits from an abstract object, which defines a number of attributes. One of them is very important, it's the existence kind, which indicates whether the element exists, or is planed, or is simulated. Each element also has a citation object defining descriptive attributes. For the tools developed by Aegis, the description keywords, description and title attributes play an important role for the proper functioning, and we have established business rules to value these fields. The wellbore feature is a feature element for a borehole. The descriptive keywords attribute contains the type of the borehole coded on 4 characters. The title contains the borehole named. The wellbore interpretation element interprets the wellbore feature. The values of the description and description keywords refers to the type of the interpretation. The possible interpretation can either lithological, stratigraphical, geological, or geotechnical, etc. for the description of the borehole intervals, or to be a reference to a set of measures, pressure meter, gamma ray, CPT, etc. To represent a wellbore interpretation, we need to have a wellbore frame representation element and a trajectory representation element which points on a MD datum element. The MD datum element represents the head point of the borehole and it's associated with a coordinates reference system thanks a local depth 3D surface element. A deviated survey representation element also is required to store the azimuth and inclination angles of the trajectory measure stations if the borehole is non-vertical or not drilled downward. This UML diagram details the way of the single-point geometry representing the head point of a borehole with a coordinate system reference and a vertical system reference. RescueML uses the EPSG standard for the coordinate systems. For the ontologies of the properties associated with a wellbore frame representation, RescueML uses several elements. We have continuous properties for supporting the measures such as pressure meter measures, gamma ray measures, or drilling parameters, etc. We have categorical properties for supporting the codes, the names, and the description of each borehole intervals according to the type of the interpretation, either lithological, stratigraphical, geological, geotechnical, etc. Each property is defined by a property kind element. String table lookup and string lookup elements are used for indexing texts describing the lithologies for the borehole intervals. The version 2.2 of RescueML makes it possible to keep the colors chosen by the geologist to draw the borehole intervals and the layers with his geomodeling software and to reuse them identically by him on GIS software. This allows the teams to share the same interpretation of the borehole intervals and of the formations. The necessary information is gathered through a graphical information set element which can contain multiple color information elements and list the discrete color map entry elements which allow to associate the right color to the right code describing the lithology of each borehole interval. The 3D GeoModel organization overview. For the horizons, RescueML uses a boundary feature element, which is a concept of a boundary surface between two layers of a lithological stack of reference according to the type of the model. A horizon interpretation element that can interpret the top surface or the bottom surface everywhere the layer exists, or either a profile top or a profile base if we want to define the boundary surface on each point of the area of interest. The Aegis tools use a triangulated set representation element, a set of thin surface, to represent a horizon interpretation. But RescueML also allows to represent a horizon interpretation with 2D grids and a set of plans. For the layers of the different type of models, stratigraphical, geological, or geotechnical, RescueML uses a rock volume feature element, which is a feature for a layer between two horizons. a stratigraphic unit interpretation element that interprets the rock volume feature. This stratigraphic unit interpretation is connected to the horizon interpretation element of the top and the bottom of the layer, thanks to a genetic boundary-based time interval which defines the chronotop and the chronobottom relations. A boundary relation element specifies if the boundary is conformable or not above and below for taking account, by example, an erosion phenomenon. RescueML offers several ways to represent a stratigraphic unit interpretation with 3D grids or Piros grids. For the different models, stratigraphical, geological, etc., RescueML uses a model element which is a feature for a 3D model of a given type. An Earth model interpretation element that interprets the model according to each version obtained along the life cycle of the project. A stratigraphic column that describes the lithological stack of reference defined for the interpretation of the model. With RescueML, it can have several columns for detailing the units, but generally the geomodeling tools can define only one set of layers for a model. Each column of a stratigraphic column is a stratigraphic column rank interpretation element. This element aggregates the set of the stratigraphic unit elements from the more recent to the oldest formation. Like for the borehole intervals, a color information element allows to keep and to share the different colors associated to the different layers by the geologist when he builds the 3D geomodel with the other softwares using RescueML version 2.2. At the left, this view shows a model with a stratigraphic column with two ranks. The first ranks define two layers with a subdivision of the unit B. Then the ranks 2 has 3 layers. A normal fault separates the geological compartments. For a fault, RescueML uses a genetic boundary feature, a fault interpretation, and a triangulated set representation or a tree grid to represent the fault. RescueML allows the possibility to specify the contact between the fault and the horizon crossed by the fault. That allows to software B to modify the depth of a fault and to adjust the geometry of the layers. Now I will present you a few results of the tests realized on old projects. The first example concerns an extension of the Guadeloupe Harbor on a shoal area. With a GTM multilayer, I have realized a 3D geotechnical model with 9 layers. Thanks to RescueML Builder, I have exported all the model in the RescueML format. Then with our tool RescueML CAD, I have successfully imported all the model with the right color for each formation without loss of data. The GDM view is slightly different of the Civil 3D view because we have an exaggeration of the Z-scale under GDM, but no deformation under Civil 3D. The orientation of the views are different and mid-ground is represented only on the Civil 3D view. The boreholes import under Civil 3D thanks RescueML CAD. The boreholes to import can be selected according to several criteria: the existence kind, the interpretation of the model, the orientation of the boreholes, the type of the boreholes, and in function of the minimum value and maximum value of X and Y. The user can specify the section shape and the diameter of the borehole. This slide shows the result of importing boreholes into ArcGIS Pro using our new tool called RescueML GIS. RescueML GIS is an add-in for ArcGIS Pro that uses the same RescueML files as those used to export boreholes in Civil 3D. This test was performed using data from the Hinkley Point EPRC project in the UK. As with Civil 3D, we can import the boreholes with different trajectories and different interpretations. The orientation of the 3D view allows us to guess the geometry of the layers. The colors of the boreholes intervals are the same as the GDM model. Since 2019, we use RescueML Builder and RescueML CAD in production. The first project that has benefited was a study for Grand Lyon New Subway line. A geological model has been realized under GDM multilayer with longitudinal cross-section along 8 different paths, starting from the city hall of Lyon of the Bellecour Place and ending at the train station of Alais in Tassa-la-de-Billune. After the import of the model and the boreholes under Civil 3D, then the obtained drawing has been imported under Navisworks with other elements of the project, such as the tubes of the subway and the boxes representing the underground train stations modeled with Revit. This image shows the geological horizons of the top of each layers on the vertical cylinders as the boreholes drawn with an exaggerated diameter, 2 meters of diameter. The project of the renovation of the Charles III district at Monaco. This project is an example of the challenges of the geotechnical project in urban environments with a complex geology and a high risk of instability requiring the use of a high-precision model. This slide shows the aerial view of the geotechnical model realized at the mesh of 1 by 1 meter thanks GDM multilayer. On this slide is a 3D view under Autodesk Civil 3D of the boreholes below the digital terrain model. To conclude about the Aegis tools and the strengths of the RescueML version 2.2 format, we have realized 3 interoperable tools based on the RescueML version 2.2 format. RescueML Builder for exporting the borehole data on 3D models realized with GDM multilayer, RescueML CAD for importing the boreholes and the 3D models to the Autodesk softwares, RescueML GIS for the import of the boreholes under ArcGIS Pro. The import of the 3D models is yet to do. Because the version 2.2 of RescueML will issue officially this year, the tools like GoCAD QA and Earth Vision using the RescueML version 2.0.1 will be nextly upgraded and we can use them for our projects. And on the last but not the least, Jean-Luc's company, a producer of drilling materials and softwares, will allow soon to its clients to export their borehole data in the RescueML version 2.2 format. Our use cases show that RescueML version 2.2 is an universal format for geosciences. The strengths of this format are numerous. Its technology and its level of semantics is very high. It's a free standard, very well documented, with API library available on the Energistics website. All the developers can take this format and use it with success. The final release of this format will be available on 16th March 2022 on the Energistics website. Thank you very much for your attention, and a special thanks to Dr. Bettingsu Kola and Mrs. Brisilia Labour. If you have any question?
Thank you for this presentation. Do we have questions in the room? Yes.
Yes, Florent Robert from the French Tunnel Study Center. I would ask, how do you deal with uncertainties in your modeling? Because I see deterministic layers, but as we saw in the previous presentation, we have some uncertainties, and we can have for layers or for bedrock uncertainty of a level. So how do you modelize that? How do you deal with that?
I realize my 3D model with GDM, multi-layer software of BerGM. And there is a methodology with GDM to check the boreholes with the horizon. And we consider if the limit between two intervals of different layer in the borehole of the borehole is present an error of more 1 meter from the calculated horizon by the model. And I have to consider if the borehole is has an error, or if the calcul, the build of the model is wrong. So the model is obtained with a cycle of test on error, and finally all the boreholes taken into account into the model respect maximal error of 1 meter below or above the horizon, each horizon. It's possible that there is a few boreholes which it's not possible to reduce the error with the model. Then we discard this borehole, and we have to clearly in the report of my work for the client to do we have discarded this borehole, etc. for any reason. But we have not represented the uncertainties. I think it's possible to represent uncertainties with ResQML, the ResQML format, but that needs to a lot of work for reflection about that.
Any other question in the room? Well, I do have one myself. We had a interesting first presentation reflecting the working group in mind on terminology and to work on harmonizing the definitions used in Geotechnics. Do you intend to work with them to define ResQML? Because when you exposed the conceptual model, you were referring to specific concepts, and those concepts are now put together and defined within the mind working group. So do you relate to that group?
J'ai pas compris ta question. Ah, j'ai pas compris ta question.
La première présentation avec Michael Wolfis.
Oui.
Il a raconté leur niveau de terminologie.
Oui.
Ils s'étaient mis tous d'accord sur la définition des termes. Et là, dans la présentation du modèle conceptuel de ResQML, les termes, est-ce qu'ils sont reliés à ce groupe de travail-là? Est-ce qu'il y a un lien entre les deux groupes?
2 years ago, I participated with a group of mine directed by Michael Bofis. Unfortunately, my colleague Bastien Lueo and me, each time we ask about RescueML, Michael Bofis, oh no, it's oil and gas format, no for geotechnics. So we have never the possibility to speak with a good debate with him. And,
that might be.
At Aegis, we have clients on demand for that, and we decided to use RescueML for our production because no, it was difficult to participate at mine.
Mm-hmm. There's a good opportunity now that 2 years later, then their working group has now finalized their work and written their report, and that you also will publish the conceptual model in March to align the different definitions for the concepts. I think it's a good opportunity, not to stick at the file exchange definition, but on the atomical concepts definitions. What do you define as a borehole, as uncertainty, which kind of, what units do you use, and so on. All these definitions meant to be published in the Benic Smart Dictionary. So that would be a common reference between RescueML and their work. That's idea for future work.
Yeah, the part of the RescueML format we exploit is only a little part of the RescueML format. We think it would be a good thing if RescueML and the IFC can go in the same direction, and why not to merge? A strength of the RescueML is the technology and the organization of the data and metadata. We have two separated files, and it's a good thing to separate it, metadata and data. The metadata, the data, X and Y, Z, etc., are in a binary file. It's more, it's not heavy compared to one file in text. So it's also a good thing for the planet to store a small volume of data. And you have the possibility to access directly to one top-level element, one borehole, with this data directly with an IFC file. I think you need to read all the file and to charge your computer, the memory. It's like the language, French, German, Chinese, etc. It's a richness. So to have several formats, it's very important to have several formats because that creates a richness and for everybody.
We have a Michael online requesting the...
Yes, thank you for giving me the possibility to speak. Hello, Jean-Marie. Thank you for your presentation about RescueML. I just wanted to answer what you said about the connection with mine. I mean, you know, it's the reason I didn't push for now RescueML in the project is this one. I mean, for Beam, there is a standard that to me is the one that should be used, that is IFC. And this is a standard that is not perfect. It has a lot of capacity, but also some drawbacks. But I think this is the one that the community shows. And that was, I cannot imagine to propose something that is not compatible with IFC. So that's the first thing. I wanted to build something that is compatible with IFC. The second thing is about the data we have in geoscience that are described in book A, book B, and book C. These are, most of them are already available in GIS, and the way to expose them is through OpenGIS standards, the one from OGC. So my responsibility as a leader of the Mine Geotechnics group was to propose something that fulfills the requirements of the world people. The things that to do the connection between GIS and BIM was identified as something that was relevant and something that should be pushed and useful for everyone. That was the reason we pushed into that direction. Regarding RescueML, I think that's something that is really relevant when you deal with geomodeling tools. And for now, we have people in mind that do not use geomodeling tools in order to build their models. They are relying on tools like AutoCAD, Civil 3D. And I didn't want to enforce them to build some Schlumberger or Petrel or something like that in order to do their job. I just wanted to help them to make it better. So that's the reason we go into that direction. The other one is that we cannot address everything for now. I try to do it. But this is not, the door is not closed in order to connect with RescueML. I mean, that's something we may discuss in the future, and I still believe that RescueML is something really relevant. So that was to answer the reason we chose this path for mine.
Well, thank you, Michael, for these precisions. It's time to switch to our fourth presentation for today. It's named Reduction of Uncertainties in the 3D Geological and Geotechnical Models by Considering Geophysical Investigation Results. And this presentation will be done by Ms. Rie Kudo. She's engineering geologist at Ohio Corporation in Japan. She is director of Japan Society of Engineering Geology and vice chairman at the Common Schema Committee of BNXMAT Japan. And she's a member of the IFC Tunnel project for BSI. And I think she's online. Excellent. And
yes, hello. Can you see me and hear me?
yes, absolutely. Thank you for being with us. And can you share your screen?
Yes, just a moment, please. Can you see my presentation file?
Not yet, shouldn't be long.
Now I share my presentation file. Can you see it?
It's processing.
It's on the way from Japan.
It shouldn't be long.
Yeah, we have it. It's shared, it's okay.
All right. If you can switch to full screen would be best.
Screen. Change the screen.
I mean full screen instead in a presentation mode. Here we go. Thank you. Up to you.
Okay, just a moment, please. Well, hello, I'm Rie Wada, a geologist at Oil Corporation. I'm gonna talk about reduction of uncertainties in the 3D model by considering geophysical investigation results. First, I'll talk about geotechnical risks which affect infrastructure life cycle. Next, I'll briefly talk about geological and geotechnical model requirements. And I'll mention the advantage of taking geophysical survey results into account modeling. Then I will show a case study. And finally, I will talk about the conclusions. First of all, I'd like to talk about geotechnical risks that may occur throughout the life cycle of infrastructure. These photos show examples of geotechnical risks like road collapse during a subway tunnel construction in an urban area. Face collapse and deformation occurred during tunneling. Road collapse due to liquefaction, and debris flow caused by the collapse of the upstream embankment. The chart shows geotechnical risk factors of 75 incidents surveyed by the Geological Risk Society of Japan. Okay. 20% of the cases were due to the unpredictable geological complexity. The other 18% of the cases were caused by human factors like misunderstanding, misjudgment, lack of knowledge, inadequate communication, and project implementation issues. These risks can be reduced by collectively assessing and understanding the situation and taking necessary actions. According to the past cases, to prevent incidents, geological and geotechnical models should represent reliability of the model itself according to the type of business. Illustrate the geotechnical risks estimated from the model. In this presentation, I'm gonna show our study that uncertainty in the geological and geotechnical models can be reduced by interpreting the geophysical survey results. I'd like to show you an example of using geophysics in geotechnical modeling as a complement. In this particular example, we used 3D microtremor array measurements, which builds a S-wave velocity distribution from small vibration from traffic noise or wave. Vibrations are measured using seismographs placed on a ground surface. The survey is more cost-effective than drilling and obtains 3D velocity distribution. Commonly, layer interfaces detected using drilling are connected to build a geotechnical model. If we have geophysical survey data, the interpretation can be done by tracking the corresponding isosurface, like the red dashed line. Because of uncertainty, there may be discrepancies between the drilling and geophysics. In such a case, we can use co-kriging. Co-kriging is a geostatistical tool to do spatial interpolation, considering multivariate spatial correlation. The method allows us to use different kinds of data, for example, drilling and surface wave velocity in this case, to get a more reliable and reasonable geotechnical model. This shows how co-kriging works in geotechnical modeling. The true model on the left was numerically synthesized. The color represents the depth of the bedrock, for example. The true model was sampled to make drilling data shown on the bottom middle. In this example, drilling were done at only 15 locations. Simply interpreting the drilling data by ordinary kriging produced results shown on the bottom right, which poorly estimate the true model. Clearly, we have too sparse and too small numbers of samples. Then, geophysical data was generated from the true model, smoothing and adding errors. The top right figure shows the interpolation result using both drilling and geophysics by co-kriging. Drilling data used in the analysis were the same 15 samples. As the figure shows, geophysical data significantly improved the result, even using a small number of drillings. The results will estimate the true model, especially between drillings. So by using geophysics, we can have a better picture of the subsurface with a relatively small number of drillings. This helps to keep the survey cost low. From now on, I show a case study using the method demonstrated in the previous slides that geophysical survey results contributed to making a reliable geotechnical model. The 2011 earthquake off the Pacific coast of Tohoku severely damaged underground infrastructure. Roads, gas, water, and sewer were not serving for months. A highly accurate model was required. Such a model can contribute to quick recovery, countermeasures, and preventing further disasters of the vital infrastructure facilities such as roads and sewers. However, it was challenging to interpret discrete point data such as borehole data to obtain an accurate model. So, in this case study, a geotechnical model based on borehole data was updated by using the 3D microtremor array survey data, and also the model was validated by comparing simulation results and actual damages in the past earthquakes. The study was conducted in a local city on a coast near Tokyo. This is one of the geotechnical models representing the distribution of SPTN values. The area is mainly composed of sand and silty sand, which have relatively low N values. The 3D microtremor array survey was carried out in the pink area. The pink filled area in the left figure indicates potential area of buried concave structure backfilled with loose sediments, which are expected to have more severe damages of earthquakes. The orange lines and red circles on the two maps indicate the locations of damaged roads. Also, small squares with various colors represent the collapsed and damaged houses. As shown in the figure, severe damages were recorded in the pink filled area. Therefore, accurate modeling of the concave structure and verification of the relationship between liquefaction and the structure was required. The data acquired in the survey were analyzed and obtained a 3D S-wave velocity distribution by inversion. This shows the Boxer model of the distribution. Low S-wave velocity areas shown in red can be the indication of concave structures filled with loose sediments. The two contour maps show the vessel depths of the concave structures filled with loose sediments. The left map is estimated only from discrete points such as a borehole log collected at blue points. The right one shows contour map updated using 3D microtremor exploration results. This contour map depicts more detailed feature of subsurface structures. For example, a plateau here and a valley here. Now, the subsurface structure obtained using drilling and geophysics are compared with damages of past earthquakes. The left figure shows the S-wave velocity distribution from the ground surface to a depth of 5 meters, and the damage distribution is overlaid. We can see that damaged road and houses are mostly located in a low velocity zone. The right figure shows the damage map overlaid on the depth distribution of Vs equal to 200 meters per sec, which is an indication of the host material. Red and dark colors indicate deep host material and thick deposit. There are many red lines in the dark area in the middle. This means that sand boring occurred where the loose deposits were thick. Therefore, if we can estimate the thickness of deposit layers, we can predict where these damages likely occur. Finally, 3D geotechnical model with the horizontal resolution of 50 meters and the depth resolution of 1 meter was created and liquefaction risk was evaluated. The red area shows the high possibility area of this liquefaction. The left figure shows the risk calculated based only on drilling, and the right figure is the updated one considering the geophysical survey results. You can see that the area surveyed initially had no risk, this area, but the area was categorized as high risk after incorporating geophysical data. The updated risk well agrees with the drainage pipe damage shown in the blue dots, caused by the 2011 earthquake off the Pacific coast of Tohoku. This means that a reliable geotechnical model can be created by taking the geophysical survey data into account, and it enables quantitative risk evaluation of infrastructure facilities. Furthermore, we have been developing a method to represent uncertainties in 3D models. The figure is an example. S-wave velocity values are drawn translucently where reliability is low. This kind of visualization will enable stakeholders who are not experts in geology to understand the uncertainty. Well, conclusions. Reliable geological and geotechnical models help reduce risks. In other words, model needs to include meaningful reliability for the purpose, clarify the uncertainty, and represent the risks anticipated from the model. In this presentation, we demonstrated geophysical survey for detailed interpretation of subsurface conditions, updating geological and geotechnical model considering geophysical data. That resulted in reduction of uncertainty. That is, geophysical data significantly improved the model, especially for spaces between drillings. Liquefaction risks based on the model incorporating geophysical data were agreed with the actual damage caused by an earthquake. Reliable geotechnical model can be created by taking geophysical survey data into account. Finally, it enables quantitative risk evaluation of infrastructure facilities. Thank you for listening.
Thank you for this presentation. We have time for one question, maybe the room. I do have one question myself. Considering the previous presentations about exchanging information, geotechnical information, did you have a chance to experiment exchanging this information, this voxel information with other actors? And for example, did you try to use RASQML or even IFC to exchange that information?
Yeah, we tried to exchange data in in my company, but in offshore we haven't experienced it yet.
Okay, thank you. Time to conclude the session. Conclude la session. Well, if we don't have any other questions, it's time for us to close this session. It's time to thank our hosts and our different presenters. Thank you for being with us. And we'll have, yes. We'll be back in 30 minutes in the same room for the next session. Thank you.